Let's suppose that we have a function, y equals, well, let's say 9 minus x squared. And we want to look at, let me go ahead and sketch it here, do a rough sketch. Okay, so here we go, something like this. And what we want to do is we want to find a rectangle bounded by the x-axis and this curve that has the largest possible area. That's what we want to do. So given that this is the function. So in other words, we want to find this rectangle here. Now, so what we're trying to do is figure out, well, what does x need to be so that when we go up and hit the graph and go over and back down, we get a rectangle with the largest possible area. Where do I need to go? In other words, how far over? Does it need to be way over here, close to the edge, or close to the origin here, tall and skinny, short and elongated? How does it need to be? Well, here's what we've done. We've drawn the picture here. And of course, this is x right here, and this is y. So the area of this rectangle is, now, here's what we got to think about. We've got two parts to this. We've got x here and x here. So this length here is actually 2x. But we don't need to think about that, because what I'm thinking is we will just optimize this little rectangle here. In other words, I will use this as my objective, right? X times y. That's what I want to take the derivative of. And then I recognize, well, that will give me the value for x, and if I actually want to find the length here of the rectangle, I just double it. Because of the symmetry, right? There's symmetry going on here. So I'll just do that. I'll just say, okay, the symmetry. Now, the area is going to be 2 times this, 2 times x times y. That's the area that we're actually looking for. Okay. But I'm just going to focus in, for simplicity's sake, on this one rectangle, this one little rectangle right here. Now, we have a constraint, and our constraint is that y equals 9 minus x squared. That's our constraint. That's going to help us to eliminate one of these variables. In other words, I've got area equal, or not really eliminate, but make a substitution, because I've got x times y. Well, y is equal to 9 minus x squared, so this is x times 9 minus, times 9 minus x squared. Yeah, there it goes. That's the area. This is what we want to differentiate. This is our objective function right here. Okay? So here's what we've got. We've got area equals 9x minus x cubed. Now I'm ready to differentiate. So here we go. Let me get some room over here. I've got dA dx is equal to 9 minus 3x squared. Yeah, there we go. Now I set that equal to 0. So I've got 3x squared equals to 9. Just did a shortcut there, skip the step really. So setting this equal to 0, or saying 3x squared equals 9, same thing. Now if I divide, I get x squared equals 3. And then I just square root it. Now I'm going to just do the positive root here, right? So I've got x equals the square root of 3. Well, it looks like what we found is we found what we're looking for. We found what will give us the optimal area, okay, when x is equal to the square root of 3. Now let's find out what y is in that case. So we've got y is equal to 9 minus the square root of 3 squared, which that gives us 9 minus 3, which equals 6. So it looks like if we choose x to be the square root of 3, then y is going to be 6, and that's going to give us the optimal area. Now the area of this little rectangle is going to be 2 square roots of 3 times 6. In other words, 12 square roots of 3. That will be the optimal area. Now, so the question might be, how do we know this is the maximum and not the minimum area? So we can always go back. Now look what we can do. This is the derivative right here. This is the derivative. So let me get the second derivative. Okay, here's the second derivative. The second derivative is going to be negative 6x. Okay, now I'm going to take my critical number right here and plug it in there. So I've got the second derivative at x equals the square root of 3. Now let's see here. We've got negative 6 square roots of 3. Now that is definitely less than 0. And remember, when you plug in the critical number into the second derivative, if it's negative, that corresponds to a maximum. So what we found is, we found where a maximum occurs, and that is when x is equal to the square root of 3.